Welcome to This Explainer. Today, we're breaking down the source material behind a fascinating, inevitable, and honestly almost entirely ignored reality of modern engineering. Because here's the undeniable truth about infrastructure. Every single dam ever built will eventually stop being a dam. It's really just a matter of physics and time. Concrete degrades and weakens over the decades, sediment continuously piles up in the reservoirs, shrinking their capacity, geological conditions slowly shift around them, and eventually, the sheer operational costs to maintain these aging behemoths rise to an absolute breaking point. So sometime in the future, the massive Three Gorges Dam in China is going to reach the end of its lifespan. And that brings us to a monumental engineering puzzle.
Okay, let's dive into this, because this isn't some abstract, far-off sci-fi scenario. At some point, whether that's 50 years, 100 years, or 200 years from now, this colossal structure will need to be safely dismantled. But here's the truly staggering part. The engineering required for a controlled decommissioning of a dam of this insane scale has never actually been attempted. It's a completely unengineered reality. Nobody is talking about how to actually do it, and the sheer logistics involved will require us to solve problems that humanity has literally never faced before.
To give you a sense of scale, let's anchor this with a number: 2000. Now, dam decommissioning itself is actually a growing field worldwide as older infrastructure ages out. In the United States alone, engineers have successfully removed over 2,000 dams since the 1990s. But those were small projects. We're talking about dams that are typically 5 to 30 meters high, holding back maybe just a few million cubic meters of water. Taking them down was complex, sure, but it was highly manageable using standard, well-tested engineering practices. Those methods, they simply do not apply to our topic today.
We are talking about a structure that towers at an immense 181 meters high. That is a radically different universe of engineering. A controlled decommissioning at this gargantuan scale has never been attempted, it's never been planned out in any real detail, and based on publicly available information, it's never even been seriously studied. We are flying completely blind into what will be one of the largest infrastructure removals in human history.
Problem 1. The massive draining challenge.
Now, what's really interesting here is the staggering amount of water involved. Before you can even think about touching the concrete, you have to figure out what to do with the reservoir. The Three Gorges Dam holds back an almost unfathomable 39.3 billion cubic meters of water. To put that into perspective, that is enough water to fill more than 15 million Olympic swimming pools. And you can't exactly just throw open the floodgates and let all that rush downstream. If you did that, you wouldn't be decommissioning a dam. You'd just be triggering a controlled catastrophic failure, completely obliterating and flooding absolutely everything in its path downstream.
So engineers have to carefully calculate the drainage. Let's compare the options. If you were to use the dam's maximum discharge capacity of 116,000 cubic meters per second, you could theoretically drain the entire thing in just 4 days. But as we just established, that fast drain guarantees a severe, deadly flood. To execute a safe drain, you have to lower that massive reservoir incrementally. You'd need to release water at a non-flooding rate of perhaps 10,000 to 20,000 cubic meters per second above the normal river flow. At that highly cautious, safe rate, it would take months, if not years, to safely empty the basin.
Problem 2. Unprecedented landslide risks. Here's the catch. By solving the water discharge problem with that slow, safe drain, you instantly create an entirely new, potentially much deadlier geological disaster along the shores. Let's walk through the exact physics of this chain reaction. Step 1, the gradual drawdown begins over those required months. As the water level slowly drops, Step 2 happens, the retreating water line exposes the riverbank slopes. Now remember, these slopes have been completely saturated, just soaking in water for decades. Step 3 is where the disaster actually strikes. When you remove the water from the reservoir, you are removing the physical weight and pressure of that water that was pushing against the dirt and rock. Engineers call this hydrostatic support. Without that water acting like a giant invisible hand holding those heavy, waterlogged hillsides in place, you trigger massive slope failure. A 175 meter to zero drawdown will profoundly and violently destabilize the riverbanks.
I really want this stark realization to sink in. The landslide risk during decommissioning might exceed anything experienced during operation. During normal operations, the dam's water levels fluctuate by about 30 meters annually. And you know what? That already causes significant geological stress. So dropping that level a full 175 meters all the way down to zero, that is a geological nightmare on a totally unprecedented scale.
Problem 3. The toxic sediment dilemma. Okay, let's say you managed to safely drain the water and somehow survive the collapsing hillsides. Well, now you have to face what's been lurking at the very bottom of the reservoir for decades. Behind the concrete walls of the Three Gorges Dam sits an astonishing accumulation of sediment. And we're not just talking about harmless mud and sand here. It is a highly toxic sediment cocktail. For decades, the dam has acted as a giant trap for heavy metals, industrial chemicals, agricultural pollutants, and raw organic waste flowing down the Yangtze River. As the water drains away, billions of cubic meters of this hazardous material are suddenly sitting right there, exposed to the open air.
This presents an absolutely impossible choice for future engineers. Do you leave it or do you remove it? If you leave the sediment in place, you've just created a permanent environmental hazard. Every time it rains, the water will wash over it, leaching those concentrated toxic pollutants directly into the groundwater and carrying them right downstream. But what if you decide to remove it? Well, actually, scratch that. It's practically logistically impossible. There is currently no mechanism, vehicle, or strategy capable of excavating and safely disposing of billions of cubic meters of toxic sludge.
The harsh reality is that dealing with this contaminated sediment means dismantling the dam is no longer just a demolition job. It transforms into a multi-decade environmental remediation project. It's going to be a massive, multi-generational cleanup effort just to ensure the exposed riverbed doesn't completely poison the surrounding ecosystem.
Problem 4. The economic transition.
So, we've talked about physics, we've talked about geology and chemistry. Now we need to zoom out and look at the massive infrastructural void that decommissioning will leave behind. 22,500 megawatts, that is the massive amount of clean generating capacity the Three Gorges Dam currently produces. You can't just remove that kind of power from the grid first and casually hope to build replacements later. Society still desperately needs that electricity. Before the dam is ever taken offline, all 22,500 megawatts must be completely replaced with functional operational infrastructure, whether that's sweeping solar farms, vast wind networks, or entirely new nuclear facilities.
And that leads us to this truly staggering estimated cost, $100 billion to $200 billion. When you combine the cost of building that massive amount of replacement power, the highly complex engineering of the decommissioning itself, and the multi-decade environmental remediation of all that toxic sediment we talked about, the financial burden is just breathtaking.
So the crucial point is this. The decommissioning cost could easily exceed the original cost to build the dam in the first place. This immense financial burden will have to be budgeted, carefully planned, and flawlessly executed by whatever government happens to be in power 50 to 150 years from now.
The intergenerational belt.
Let's look at the broader philosophical implications of this megadam's life cycle, because it really forces us to think about how we build the world today. Consider this wild paradox. The generation that built the dam won't be the generation that decommissions it. The visionary engineers who designed it will not be the ones tasked with solving the unprecedented technical problems of dismantling it. And the politicians who approved it and celebrated its completion, they will not be the ones bearing the extraordinary cost of removing it.
Ultimately, the dam operates as an intergenerational transfer. Benefits to the present, costs to the future. Right now, society gets all these massive benefits: cheap, clean electricity, improved river navigation, and incredibly vital flood control. But we are essentially taking out a massive loan. We are borrowing against the staggering environmental, geological, and financial costs of tomorrow. The bill for all this present-day utility will, inevitably, come due. And the future gets no vote. The people who will have to deal with the tricky draining process, the terrifying landslides, the mountains of toxic sludge, and that multi-billion-dollar price tag, they haven't even been born yet. They have absolutely no say in the infrastructure debt being handed down to them. Which leaves us with this final, provocative thought. Is decommissioning a question we should be asking right now before we build the next massive piece of infrastructure? Let us know what you think about planning for the end of a megastructure's life. And be sure to subscribe to see our next explainer, where we'll be breaking down the source material to compare the hidden risks of other massive megastructures around the globe. Thanks so much for learning with us, and we'll see you there.